Welcome to the second unit for A2 Computer Science, Communication and Internet Technologies. Now, there are two major parts of this particular section. One is to understand the need for protocols during communication. How do we enable different devices to talk to each other? And the second is the use of circuit and packet switching. In this section, we're going to be looking at the need for protocols during communication, how you can actually implement a protocol like a stack. We're going to delve deeper into the TCP/IP protocol, especially the 4 layers of application, transport, internet, and link. We're going to understand the purpose and function of these layers and how an application can use these to send a message over the internet from one host to another. We're also going to be looking at different types of protocols like HTTP, FTP, POP3, IMAP, SMTP, and the BitTorrent protocols. The second part of this unit focuses on circuit switching and packet switching. So you need to understand the benefits and drawbacks, how a router enables packet switching, and the use of packet switching to pass messages across the network, including the internet. So this unit is going to be an extension of the communication unit from AS level, where we looked at networking devices and the internet. So we're just going to go a bit more deeper into the protocol side of things. So let's start with understanding why a protocol is essential for communication between computers. And as you know, there are different types of computers. There are different types of processors, instruction sets, different types of software. And to enable different types of devices to talk to each other, we need to have a set protocol. So let's start with a prior knowledge check on these. You should know this already from last year. What is meant by a protocol? What is meant by topology? What is meant by peer-to-peer? And why are rules and formats important when sharing data? So do pause the video and have a bit of a think about these questions before continuing. If you don't know the answers to these, my suggestion would be to find that out, because some of these terms are going to be used throughout the next couple of videos. So let's start with protocol. A set of rules governing communication across the network. And these rules are agreed by both the sender and the receiver. So when you're answering this type of question, you need to make sure that the set of rules governing communication across the network, that part is often very clear. But the second part, that these rules are agreed by the sender and receiver, that's the bit that students often miss out when they're writing an answer. So make sure that when you're giving a definition type answer to protocol, you include both parts. So topology should be pretty clear, a method of connecting different devices together, an arrangement of devices in a network. Remember star, bus, all of those kind of things. So peer-to-peer basically is a network in which each node can share its files with all the other nodes. So therefore each node has its own data. There is no central server. And finally, why are rules and formats important when sharing data? Well, when you have a sender and a receiver of data, both parties need to agree to the same set of communication rules for successful communication to take place. If one party tries to do something differently, then that can lead to miscommunication or data collision, and therefore it's essential for rules to be followed. And this is where the need for protocols comes into play. So let's start by looking at the requirements for communications. There are initially 5 requirements for a data communication system. You've got to have a sender, you've got to have a receiver, you've got to have a transmission medium, a message, and a protocol. Now, if you don't have any of those 5, communication does not happen. A message can only be transmitted if there is an agreed protocol. Do they share the same language? Do they know when to stop talking and when to start talking? Those kind of things. A data communication system may consist of an isolated network or a connected network, because within a system itself, different components might need to communicate with each other. So protocols are of the utmost importance. And why so? Because they define the rules that are needed for any means of communication. Now on screen, you can see a simple communication method, and chances are that when you were little, you might have built something like this as well. 2 cans with a piece of string, Can you think of rules for this type of communication? So pause the video and have a quick think. Okay, you must have thought of some rules, and perhaps in those rules you must have a mechanism to let the other person know when to start talking and when to stop talking. You must have words like over, over and out, and you might have decided that perhaps the language of communication would be English, or maybe that was assumed. Or perhaps you had your own encoded language. Children often, when they're experimenting with this, have their own coded language, so a bit of encryption going on there as well. Whatever your rules for this type of communication methods, they probably are valid. But why are these rules needed in the first place? Because think about what would happen when two people talk at the same time. In networking terms, we call it collision. Why? Because in English, in plain old communication, vocal communication, what you might find is that when two people are talking at the same time, both parties might not actually understand each other. In networking terms, this is called a data collision. And this type of situation needs to be avoided. Therefore, we need regulations and rules on how to communicate over a computer network. And an example could be a remote login, telnet, or an FTP, or an email protocol. In the absence of protocols, devices will not be able to understand the electronic signals that they send while communicating over network connections, because they might misrepresent what these electronic signals mean, and that can lead to all sorts of issues. So protocols are a set of rules governing the way that devices communicate with each other, and thinking back to what we said earlier, both sender and receiver need to agree to this protocol for successful communication to occur. Now, with networks and the internet, we need to allow computers to talk to each other. That's a bit of a given. And these computers must talk to each other in a way that the receiving end can understand the message. There are many different protocols out there, and each defines rules for a specific communication type. For example, FTP enables file transmission. HTTP allows communication of web-based data over the internet. POP3 and SMTP are email related or messaging related. So each of these protocols has a specific purpose. So let's delve into protocols a bit more deeper. Let's start by looking at the port number. The port number is an application endpoint or process-specific communication endpoint which is attached to an IP address. Now think about it this way. To make sure that the data is dealt with by the correct program, for example, you want a website, then you need to make sure that the request goes to the right web server. If you're sending data over Skype, you need to make sure that it's received by the correct Skype server and not anyone else. In order to ensure this actually happens, this proper activity actually occurs, you need to add a port number. Now, each application will have a port number associated with it. For example, a web server is port 80, a Counter-Strike game is port 666, and combining an IP address with a port gives us something called a socket, which allows a direct connection to a process or an activity on a server. And think about it this way, that a web server can have multiple applications running on it, and each application could be connected via a specific port. And when you combine the IP address and the port, you can directly access that application on a web server. Now, both of these pieces of information combined together is called a socket. Now, that's all you need to know from the technical point of view at this point in time. But this can also cause issues. For example, if we're using a particular port or a particular socket in this case, and then you have multiple devices trying to communicate with that port or that socket, that can lead to collisions. And it's possible to end up sending data packets on the same channel at the same time. And this, as we know, is called a collision. And if you remember from year 12, CSMA-CD, that particular protocol can help with collision detection and can help resolve that. Now on screen, you can just see that little flow chart of how it works, how we assemble a frame, how there's a timeout, how we can update the transmission counter when a collision is detected, and keep resending until the transmission counter reaches the max. And if it reaches the max, at that point in time, we abort the transmission because the line quite clearly is very busy. We'll revisit this protocol again when we look at some common protocols later on. But before we do that, We're going to look at how protocol implementation can be viewed as a stack where each layer has its own functionality. So a protocol is made up of several modules, and each of which is responsible for a certain subtask. And the idea of dividing a protocol into subtasks can be viewed as a stack structure where each subtask is an individual block. So if you're looking at the diagram, you can probably see that you've got the application layer where the base application lies, then you've got the transport layer, then you've got the internet layer, and then you've got the network access layer. And when you send data that way, the receiving computer, the data also goes through the same layer. So the network access layer obviously is first, internet, transport, and application. Now the transmission control protocol / internet protocol, or TCP/IP, these layers act as a kind of stack. Now TCP/IP protocol defines how electronic devices should be connected over the internet and how data should be transmitted between these devices. The TCP part, or the transmission control protocol part, is responsible for breaking data down into small packets before they can be sent over a network, and for reassembling these packets again when they arrive. The internet protocol part takes care of the communication between different computers. It's responsible for addressing, sending, and receiving the data packets over the internet. A TCP/IP normally has that four-layer system where you've got the application, transport, internet, and network layers. So these layers break the process down into manageable self-contained modules. And this process is also known as decomposition, which you're familiar with. And this makes it easier to develop and easier to make software and hardware compatible with each other. So why is a protocol like a stack? Through the use of layers. And each layer operates in the last in, first out format. So everything is layered on top of each other, just like a stack. So let's kind of delve a bit more deeper into these layers and show a true understanding of the TCP/IP suite. So let's start with the application layer. That's the first one. This is the top layer of the TCP/IP suite. It includes applications or processes that use transport layer protocols to deliver the data to destination computers. So the application or the program, which is also known as the process, resides here. Now the application layer contains all the programs that exchange data, such as web browsers or server software. This layer allows application to access the services used in other layers and also defines the protocols that any app uses to allow the exchange of data. Now at this particular point in time, it's worth revisiting the terms packet and router. We know that messages are split up into small groups of bits called packets. For example, a web page would be split up into a number of packets before sending over the network. And a router is used to transmit these packets of data, and routers contain connections to many other routers, so when a packet arrives at a router, it decides where next to send them. Now, an important piece of terminology at this particular point in time is that packets are known as data packets at the application layer. When they move on to the transport layer, they're known as segments. When they move on to the internet layer, they're known as datagrams. And when they move to the data link layer or the network layer, they're known as frames. Because at the network layer, you will have a physical connection, perhaps like a cable or an Ethernet cable. And if you remember back from AS, when we look at the Ethernet protocol, we assemble a frame. So each layer has its own name for the data packet because it adds its own header and an extra bit of information to that header statement. So the data packet might have a sequence number at the application layer, then get an IP address at the next one, and so on. And similarly, at each layer, there are certain protocol options to carry out the task designed for that particular layer. So application layer also has various protocols as part of that. Now remember, this is not just one protocol. The application layer might have other protocols as part of that. Now, some of the popular application layer protocols are HTTP, FTP, SMTP, SNMP. Now, full forms are on screen. These protocols will probably reside in the application layer of a TCP/IP protocol suite. And as a result of this, they allow communication with the next layer, which is the transport layer. Now, the transport layer, or the TCP, receives data from the application layer above it, and there are many protocols that work at this layer as well. However, the two most commonly used protocols are TCP and UDP. So TCP, the transmission control protocol, is used where a reliable connection is required, while UDP, or user datagram protocol, is used in case of unreliable connections. The TCP divides the data, which is coming from the application layer, into proper sized chunks and then passes these chunks onto the network layer. It acknowledges received packets, waits for the acknowledgement of sent packets, and sets timeout to resend the packet if acknowledgements are not received in time. So all of that error checking that we know from AS level happens at this particular stage. The term reliable connection is used where it is not desired to lose any information that is being transferred over the network through this connection. TCP is responsible for the safe delivery of a message by creating sufficient packets for transmission, and it uses positive acknowledgement with retransmission, which means it automatically resends a data packet if it has not received a positive acknowledgement. So think back to IGCSE and ARQ, something similar to that. TCP is also connection-oriented since it establishes an end-to-end connection between two host computers using handshakes. For this last reason alone, TCP is often referred to as a host-to-host transmission protocol. And the term host, we've used it previously. This refers to a computer or device. Now, there are some steps taken when host computer, let's just say X, communicates with another host Y. Host X will first of all send host Y a packet or a segment which will include synchronization sequence bits, so the segments will be received in the correct order. Host Y will now respond by sending back its own segment containing an acknowledgement together with its own synchronization sequence bits. Host X now sends out its own acknowledgement that the segment from Y was received. Then transmission of data between X and Y can take place. Now, the next section we're going to look at is UDP, the unreliable side of things. Now, just remember, you don't need to know UDP in any kind of detail for the syllabus. This is just for your own knowledge. Now, UDP, on the other hand, provides a comparatively simpler but unreliable service by sending packets from one host to another. It doesn't take into account any extra measurements to ensure that data sent is received by the target host or not. The term unreliable connection is therefore used where minor data loss does not hamper the task being fulfilled through this connection. So think about video streaming and those kind of things. The loss of a few bytes of information is acceptable as this does not harm the user experience very much. So the process is exactly the same, request and send data, but we don't frankly care about error checking. So if there are a few packet losses in there, that's okay. The internet layer is the next one, and the main purpose of this layer is to organize or handle the movement of data on the network. Now, by movement of data, we generally mean routing the data over a particular network. So the internet protocol is used at this particular stage. So the IP part of TCP/IP comes into play here. Internet control message protocols, internet group management protocols are also used at this layer. So all we're doing is looking at the routing of things. So using the IP addresses, we work out where everything needs to go, which DNS server, which router, all of those kind of elements come into play here. So the internet layer, in essence, identifies the intended network and host. The common protocol is obviously IP, Internet Protocol, and the concept of IPv4 and IPv6, we already covered that back at AS level. Now the network data link layer, which will come up in a moment, identifies and moves traffic across local segments. So it encapsulates IP packets into frames for transmission, maps IP addresses to MAC or physical addresses, and ensures correct protocols are followed. The physical network layer specifies requirements of the hardware to be used for the network. The data link layer identifies network protocols in the packet header, TCP/IP in this particular case, and delivers packets to the network. So the summary of the IP functions are as follows. Ensure correct routing of packets of data over the internet. Responsible for protocols when communicating between networks. Take a packet from the transport layer and add its own header, which will include the IP address of both sender and receiver. And then the IP packet, or the datagram as it's known, is sent to the data link layer where it assembles the datagrams into frames for transmissions using perhaps an Ethernet protocol. So after the traffic management of the internet layer, we move on to the network layer, which is also known as the data link layer. Now these names can be interchangeable, so just be aware of them in an exam. This layer normally consists of device drivers in the operating system, the network interface card attached to the system, those kind of things. So the actual hardware layer which is used to transmit things. Both the device drivers and the network interface card take care of the communication details with all the media that they're linked to transfer data over the network. In most of the cases, this media is in the form of cables, so you have Ethernet cables, those kind of wires. And some of the famous protocols that are used at this particular layer include ARP, Address Resolution Protocol, and PPP, Point-to-Point Protocol. And if you've ever messed around with networks or read about this online, you'll probably come across these protocols as well. Now, at this point in time, it might be useful for you to just revisit the Ethernet protocol. Ethernet is a system that connects a number of computers or devices together to form a local area network. So it is a local protocol and does not provide any means to communicate with external devices. This requires the use of IP, which sits on top of the Ethernet protocol. You can probably see the makeup of a typical frame used by the Ethernet protocol in the diagram on screen. You should not be interested with preamble, start frames, inter-packet gaps, but just have a look at what goes into an Ethernet data frame. Destination, source, Ethernet type or length, the actual message, and a frame check sequence. If VLAN or virtual LAN is used, the Ethernet data size increases from 1539 bytes to around 9,000 bytes per frame. And the components that make up Ethernet data are destination MAC addresses, source MAC address, the Ethernet type or length, which is the frame length, and the frame check, which includes a checksum to provide a method of checking data integrity following the transmission of the frame. So destination, source, Ethernet type or length, and a frame check in addition to the data. That's part of an Ethernet frame. Now, putting it all together, at the application stage, you first decide what you want to do. So a web browser might use the HTTP protocol, an email client might use the SMTP protocol, a file uploader might use the FTP protocol, things like that. So these protocols are used to communicate the data that needs to be sent, and then the next stage is the transport layer, where you divide the data into packets, add things like sequence number, source port, destination ports, all of that. So the data coming from the upper layer, the application layer, is packaged in smaller chunks, which could then be transmitted. And the next level, the internet layer, it's here where you start adding IP addresses. So the route for transmission is decided at this particular stage, and it has its own protocols. And finally, the hardware comes into play, because all of these data packets with all of the sequence numbers and the internet addresses, all of these need to actually be transmitted on the hardware, which include cables and network interface cards, wireless access points, those kind of things. So the information actually has to travel on physical media to reach the target machine. And once it reaches the target machine, everything else goes in reverse. So the network element will take the data, the internet one will decode it, the transport will then repackage it and assemble it back again, and the application will then use it to display the data to the user. So what do you need to know? You need to know the 4 layers. You need to know them inside out: application, transport, internet, network. And you need to know the protocols that might be applicable at each stage and what actually happens at each stage. Now, one thing I want to point out is that at the target machine, when the data reaches this particular layer, the TCP makes a note of the sequence number of packets and sends an acknowledgement. And if the host TCP does not receive the acknowledgement within some specified time, it resends the same packet. So ARQ type approaches happen here at the TCP layer. Now, this way, the TCP makes sure that no packets get lost. If all the packets haven't arrived at the transport layer, then you're going to end up with buffering, and you're going to end up with data loss at the application stage. The protocol at every layer reads the information sent by its counterparts to achieve the functionality of the layer it represents. So it's not just a straightforward way of, okay, the network layer will send the data and everything else works smoothly. The network layer will check the data sent by the network layer. So it's only interested in the Ethernet side of things, for example, the hardware side of things. If everything works, it's okay. Then it passes it on to the next layer. So the internet layer will check the data that's been sent by its counterpart on the other end, and the transport layer will do exactly the same. The application layer will only be interested in the requests. Are the requests sent, and has the appropriate data been received or sent accordingly? Okay, that's going to be the end of this particular lesson. You should be able to tell the differences between TCP and UDP in the transport layer. You should be able to explain all the layers, what happens at each stage, how a protocol can seem similar to a stack, think about the use of layers and how they operate, and how does the TCP/IP protocol actually work, what happens at each stage of that particular process, and the various different protocols that are being used at each stage or each layer. That's all for today. I'll catch you in the next lesson.